In this video, I'd like to go over another 2D static equilibrium problem where what I'm solving for is some distance x that a force needs to be applied to in order to keep my system in equilibrium. Now this is going to be the distance from this point B, which is a pulley, that this 48-pound force needs to be applied to for the system to maintain equilibrium and not move. This is a little different than some of the other problems I've done where most of the time I've been given these distances and I'm solving for what the actual magnitude of the force is, but we're going to follow the exact same procedure. We're going to draw a free body diagram, we're going to apply the equations of equilibrium, and then we're going to solve the equations of equilibrium for x, or what this is going to turn out to. We're going to have an intermediate variable that we can then use to solve for x. So let me explain this problem, the setup just a little bit. At point A, we have some collar. Now this collar is free to move to the left and to the right over this rail. And the rail and the collar are going to be in contact with each other. Now that's going to be important when we draw the free body diagram. The other assumption we're making is the collar is massless, so it doesn't have any weight force. Now, the collar has this 48-pound force that's applied to it, and it also is attached to a rope, and on the other side of the rope is this 50-pound weight. So let's look at the free body diagram that we want to draw. When we're drawing this free body diagram, really the main place we should be looking at is point A. It's connected to a lot of the different forces we've talked about. If you draw a free body diagram of the 50-pound force, all you're going to get is the tension in the rope, which you could actually get by just observing the problem. And we'll see that in just a minute. So let's draw the free body diagram of point A. With point A, there's a couple of forces that are really easy to see. This 48-pound force that's being applied. We have this tension force that goes along the cable. We'll call this some force TAB. We don't know what this angle is. We'll look at the angle in just a minute. And there's one more force that we need. I had said that the collar and the rail were in contact with each other. So when we have two objects in contact with each other, we have that surface force or the normal force. In this case, the rail is going to be our surface. The rail is horizontal. So we need a force that's either going to go up or a force that's going to go down. It turns out for this problem, in order to counteract this tension force right here, the normal force actually has to point downward. Right? So in order for equilibrium, this tension is going to have some positive force that goes up. The normal force is going to have to be exactly the same, and it's going to have to point downward. So we'll call this my normal force. If you didn't see that and you had assumed that the normal force pointed upward, that's okay. At the end of the problem, all that means is your normal force will be negative. So you'll have a negative number, which means it actually points downward. So we have all of our forces on this free body diagram, but we can break this up a little bit more. We know, or we can solve for a couple of these variables, right? We know that this tension force in this rope right here, it's one rope, and if we wanted to, we could draw a free body diagram of this 50-pound weight, but we could also see that the only force going off of this weight is this rope. So that means we know this tension force, TAB, has to equal 50 pounds because all of the weight of that mass, or all of the weight of that block has to be in that cable force. So if you don't see it, draw a free body diagram of the weight, sum the forces in the y, and you'll get TAB is equal to 50 pounds. It's a good exercise for you to go through. Second, what is this angle theta? So let's draw a little diagram right here. This is my angle theta. This is point A. This is point B. So I'm drawing this part of the diagram. And what we have is, okay, I know this distance right here. This is 20 pounds. So this is 20. I know this distance right here. So this is x. And we have a right triangle. So we can use SOHCAHTOA. when we use SOHCAHTOA, and we're looking for our opposite and our adjacent, we are going to take this TOA, the tangent, the opposite, adjacent, and we can relate the angle to both of these sides like that. So we can say the tangent of theta is equal to 20 over x. So now we're going to have, this is how we're going to solve the problem. We're going to solve for what theta is, and after we get theta, we're going to figure out what x is. It's easier than trying to substitute this into trig functions. So now we have what TAB is equal to, we have what tangent's equal to, what theta is equal to, and let's move on to step 2. So for step 2, we're applying our equations of equilibrium. So we're going to be using the sum of the forces in the x are equal to 0, the sum of the forces in the y are equal to 0. In the x direction, I'm going to call the right positive. In the y direction, I'm going to call upwards positive. So let's start with the x direction first. In this x direction, I'm going to start with this 48-pound force. This 48-pound force is pointing towards the left. I had said that to the right is positive, so I need to subtract that force out. So I'm going to have minus 48. This normal force is only in the y direction, so it doesn't have an x component. And this TAB, if we resolve the vector into x and y components, we see my x part of the force is in the positive direction. If we go and we look at SOHCAHTOA, we know we're going to have to use the cosine. So it's going to be plus, because it's pointing to the right, TAB times the cosine of theta, and that's equal to 0. Okay, let's look at the sum of the forces in the y. Sum of forces in the y, we're going to have, again, TAB. This is pointing up. Up is my positive direction, so I'm going to add it. So TAB, that component, that's the opposite. Opposite goes with sine. So TAB times the sine of theta. We have to take in the normal force now. Normal force is pointing downward, so I subtract it. So minus Fn is equal to 0. Now, earlier I had said that TAB is equal to 50 pounds, so I can substitute that in. So now I've applied the equations of equilibrium. Now let's do step 3. Solve the equations of equilibrium for my unknown values. In this case, I don't know what theta is. I don't know what my normal force is. It looks like I'll be able to solve for theta right here. Solve that equation for theta. I could figure out what my normal force is, and I will, even though the question's not asking for that. Now, once I have theta, I can also plug it into this equation right here and figure out what that distance x is. So let's solve this equation for theta. I'm going to have 50 times the cosine of theta is equal to 48. The cosine of theta is equal to 48 over 50. And then theta is equal to the inverse cosine of 48 over 50. And I need to solve for that. So theta is going to be 16.3 degrees. Now I can put theta in right here. I can say, okay, 50, well, let's solve it for Fn. So for Fn, I'm going to bring it to the other side of the equation. I'll have my normal force, Fn, is equal to 50 times the sine of 16.3. And that's going to be equal to 14 pounds. So that's what my normal force is. And if you notice, if you had assumed that this was going upwards when you're drawing that free body diagram, then that would have been a positive, and all you would have had was a negative right here. So that would have told you, oh, the 14 pounds isn't actually pointing upwards, it's really pointing downwards. Okay, so I know my theta, I know my normal force. I can solve for this distance x. I can say that the tangent of 16.3 is equal to 20 over x. So I can say x is equal to 20 divided by the tangent of 16.3. And so I get this is 68.4 inches. So x, I think inches, yeah, inches. X is going to be equal to 68.4 inches. What this means that in order for this system to be in equilibrium for a 50-pound force, if I'm pulling with 48 pounds, then this collar needs to be a distance of 68.4 inches away from point B, which is that pulley. So hopefully this helps you understand a little bit more how to solve a 2D equilibrium problem in statics. If it was helpful, please subscribe. Click the subscribe button on the video. And if you're looking for other videos in the statics playlist, please take a look at some of the other videos in the playlist that you can see.